This is page 3 of your parametric graphing notes, the ships in the fog problem. Two ships are sailing in the fog and being monitored by tracking equipment, and a radar. The two ships simultaneously appear on the observer's rectangular screen. So this grid here represents a radar screen. And notice that its measurements are in millimeters. One ship, the Andy Daria, heretofore known as AD, first appears at a point on the lower edge that is 900 millimeters from the bottom left-hand corner of the screen. So that I'm going to draw a little red dot here to represent where the Andy Doria first appears on the screen. The other ship, the Helsinki H, appears at a point on the left edge of the screen 100 millimeters above the lower left-hand corner. So that would be over here, a little red dot for, and actually maybe, well, that's fine. I'll just use no, I think I'm going to use blue because I think it's going to show up on my graph as different colors. So Helsinki is in blue. All right. Then it says, the next bullet point here says, 1 minute later, the positions have changed. The Andy Doria has moved 3 millimeters west and 2 millimeters north. In other words, it's moving left and up on its path. The Helsinki has moved 4 millimeters east and 1 millimeter north of its previous position. Assume they will continue to move at a constant speed on their respective linear courses. Will the two ships collide? If so, when? If not, how close will they come? Okay, so if we look, it's going to be very difficult with a scale where this, when each block equals 50, to draw 3 millimeters west and 2 millimeters north. But if it's continuing at a constant rate, then if it goes 3 millimeters west and 2 millimeters north in 1 minute, then if we do 100 minutes, it should be 300 millimeters west and 200 millimeters north. So that's what I'm going to draw. 300 millimeters to the west and 200 millimeters to the north. Then we should be here, right here, at 100 minutes away from the time it first got on the screen. And I am going to draw a line indicating, and I have this nifty little pen that automatically makes a straight line, even if I draw it crooked, so that's nice. Now the next one, the Helsinki, says that it moves 4 millimeters east and 1 millimeter north. So in 100, that's in 1 minute. In 100 minutes, it would be 400 millimeters to the, I'm sorry, not west, east, and 100 millimeters to the north. So now we would be right here. And I'm also going to draw a line to represent, oops, wrong thing, draw a line to represent its path. And that one obviously needs some adjustment. There we go. There we go. Now, when we see these, as they cross the computer screen here, I'll kind of extend that out a little bit. We see that their paths indeed cross. Does that mean that they collide? Now, some of you are probably going, well, no, because they might cross, but we don't know when they cross. And that's exactly the question, is their paths cross, but are they both at that intersection point at the same time? That's the question. And that is what a parametric equation can answer that a linear, just a regular equation in rectangular or xy form cannot answer, because we need to associate time with x and y. So the first thing we're going to do is write parametric equations for each to represent the paths of each of these two ships. For the Helsinki, we're going to start with knowing what is its initial position. The initial position is at 0 in the x direction and 100 in the y position, and then it continues to move 400 or 4 millimeters to the east and 1 north every minute. The Andy Daria, its initial position is at 900, 0. It's moving 3 millimeters to the west and 2 millimeters to the north every minute. So if we let t represent number of minutes, we can write equations to represent these. So the Helsinki, we'll just start out with t is 0. When t is 0, where is it in the x direction? It's at 0. Where is it in the y direction? At 100. When t is 1, then now it's moved 4 millimeters to the right. So now it's at 4 in the x direction, and it's at 101 in the y direction. 2 minutes later, now, from the initial time, it would be 8 millimeters in the x direction and 102 in the y direction. And just looking at that pattern, how could we write an equation for x as a function of t? Well, notice every time x is just 4 times t. So x is 4 times t. Y, though, starts out at 100, and then we add 1 each time t goes up. So we could call that 100 plus t. Now I'm going to make a chart for the antidaria, and then I suggest you pause and try to write the equations yourself before I tell you what they are, because you are going to be have to be able to do this at a future time. So we start out with an initial position at 0, 100. So when time is 0, x is 0, y is 100. Then after 1 minute, I'm sorry, I just did the same one over again. That was silly. We start out with x is 900 and y is 100 or 0. Then we move 3 to the left. So now we're at 897 at 1 minute, and then 2 up, we're at 2 in the y direction. And when t is 2, now we're 3 more to the left, or 894, and we're up to 4 in the y direction. So pause now and write the equations for x and y, thinking of initial position and how much it's changing every minute. Okay, if you would like to check what you got, x should be 900 minus 3t, because every time we subtract 3 from 900 every minute. The other one should just be 2t. Y is 2t, because you're just doubling whatever t is. Now in function mode, we look at this, and we're talking about x, y. We know if their paths cross. We know, actually, that's not exactly what I wanted to write. We know where their paths cross. In parametric mode, where we have t, x, y, we know when their paths cross. So let's put this on the calculator and see what happens when we check out the graph. So if we go to the calculator here and put in these equations, so I'm going to put them on the same grid. So I'm going to push tab here, and I'm going to type in the equations. I'm going to pause for a minute, type in the equations, and come back to not waste your time. Now if you look here, I've put in for x1 and y1, I put in the Helsinki and then the antidaria for the x2 and y2. And if you're in x1, y1 and you just tab up, it'll lower the next one down. You can put in all the equations. Now one thing I'm going to have to do, though, is recognize that I'm not going to be able to see the entire graph in the window setting I have. I'm happy with t being 0 to something because time isn't going to be less than 1. But how many minutes do I need to get all the way across this grid? And do I want to see some more in my x and y window settings? So if you look back at your what we have here, we need to see x from 0 to 1,000 and y from 0 to 500. And notice it took 100 minutes to get from this point to this point for the Helsinki. So if I want to see that point of intersection, I'm going to need t to be bigger than 100. Probably 200 would suffice. So I want to set my t from 0 to 200. Right now it's at 0 to 6.28, which will show me about just a little bit of its path, but not much. So I'm going to change my t here to 200. I'm not sure if I can change the other one. Okay, I'm going to go up arrow now to this one. Oh, that changed. That's interesting. Okay, I'm guessing I'm going to have to close this and go back to my tab and go up arrow to my number 1. Okay, up arrow till I get to number 1. There we go. Up arrow to number 1. I'm going to change that one also to 200. And if I push enter, I'm not seeing a whole lot of anything right now. Let me go to the window and change my window settings. So if I change my window settings to match the grid, so 0 to 1,000, and I'm going to go ahead and do an enter value of 50 so that I have the same scale as what I'm seeing on my grid on the paper. and this was 0 to 500 and also by 50. So if I change this to inner value 50, oops, I just changed it back, 50, and then enter. Okay, there we go. Now I'm seeing 0 to 1,000. I'm seeing both of my graphs. There's this one. I don't know where the red label one is. Maybe I can show label. There we go. All right, so there's the red label. So here's the Helsinki, the Andide area. So we can see that they do indeed cross, but we don't know when they cross. So what we need to do is trace. So if I go to menu and trace, graph trace, I can trace one of the graphs, and notice at the bottom I'm seeing the X and Y position as well as the time. So now I'm at 118 minutes and so forth, keeping going. So there I am at 136 minutes. Now, if yours didn't trace, if it skipped over, which mine did the first time I did this, if it skips over and it's not tracing like every second, and I'm not sure why mine is this time, then you can, if it jumps over, then type in something that looks close and kind of play around with it till you find that point of intersection. And then two ways to look is I can switch to my red graph and also move it to the point of intersection and see if the times are different, or I could move to my red graph, which you do by up or down arrow. So now I'm on red. Notice when I switch, I'm at time as 118 point something. You can't see this very well. Let's see if I can drag this. 118 point, oh, it just moved it. I'm at 100, was it 118? Let me do my blue again and kind of go along here. That was 136. Okay, and now if I switch to my red, notice I'm at 118.36 it looks like. So they didn't get to the same place at the same time. Now how far apart were they? Well, realize that this is in millimeters. If I'm at 118 on the red, switch to the blue graph and type in 118.3, and you can see that when one graph was at the point of intersection, the other, you can see about how far away the two were. I can also, that's not necessarily the closest they came, because maybe when this one's at 127 and I switch to the red, notice they're pretty close together. 127. Okay, they are pretty close together at 127. 127, for example. They're not too far apart. Now the question is, are they far enough apart not to bump? Well, we don't know what 1 millimeter represents on this radar screen. Does 1 millimeter represent a foot? Does 1 millimeter represent a half of a mile? We really don't know. So knowing how far apart they are on the radar screen doesn't necessarily tell us how close they came. But it does look like they were a little too close for comfort. They were in the fog. They didn't see each other. At least it was a narrow miss. So this gives you an idea of how looking at two graphs in parametric form can give you additional information that you don't get when you just look at it in rectangular form.